Welcome to the module on basics of material testing. Today we will be discussing about the flakiness and elongation index test. This test is being conducted as per IS 2386 part 1. So how to calculate flakiness, how to calculate elongation, and how to calculate the combined flakiness and elongation using IS 2386 part 1 will be discussed in this module. What is flakiness and elongation index test? Flakiness index is the percentage by weight of particles in it whose least dimension, that is thickness, is less than 3/5 of its mean dimension. And elongation index is the percentage by weight of particles in it whose largest dimension, that is length, is greater than 1 4/5 times the mean dimension. The test is not applicable to sizes smaller than 6.3 millimeters. This is the control point which is required. One should keep in mind that this test is not applicable for a particle which is having a size less than 6.3 millimeters. Why flakiness and elongation index test? The test is used to determine the particle shape of the aggregate and each particle shape being preferred under specific conditions. The significance of flakiness and elongation index indicates the degree of packing of the particles of one size depends upon their shape. The apparatus required to conduct the flakiness and elongation index test are a balance of sufficient capacity and sensitivity and shall have an accuracy of 0.1% of the weight of the test samples. A flakiness gauge or a thickness gauge which will give you the passing for each type of materials, that is the thickness gauge is marked from 63 mm sieve to 6.3 mm sieve. So for a fraction of materials which is passing 63 and retained on 50 can be checked using the gauge B, that is 33.9 to 100 mm, that is the last one. And then for particles between 50 and 40 you can use the opening C. For particles 40 to 25 you can use the slot of 19.5 mm cutout. For 25 to 20 you can use 13.5 mm cutout, and so on. So for different range of materials, different size of openings are being provided to check the thickness of the aggregate which is being passed or retained in the thickness gauges. Similarly, you can have an elongation gauge or the length gauge, which is the standard gauge given by IS 2386. In the length gauge also you have a different range of particles, that is 10 mm passing 60.3 mm retain, 12.5 passing 10 mm retain, 16 passing 12.5 mm retain, 20 mm passing and 16 mm retain. That means for each type or each classification of the materials which is being sieved through a set of sieves, a particular opening is prescribed so that the material should be passing that gap with the length. Like for example, if a material is being sieved from 10 mm to 6.3, then the maximum length it can have is 14.7. That is the maximum opening size in terms of length. So if the material is retained, that means it is elongated, or else it is passing. So this is how for each set of sieves, like starting from 6.3 to 63 mm, for each range of sieves you can have what is the number of particles which is being retained on a length gauge. The table 5 of flakiness and elongation index, the table 5 which is being elaborated or which is being given in IS 2386, if you see, it has been clearly defined that the set of sieves which can be used to check the thickness gauge as well as the length gauge and the corresponding thickness and the length of the material which is supposed to pass or retain on a set of sieves. Like for example, if you have a material 63 mm passing and 50 mm retain, then your thickness gauge should be 33.9 and the length gauge should be 81. That means the maximum length allowed is 81 millimeters and the maximum thickness allowed is 33.9. And if minimum thickness is allowed is 33.9. If your sieves are between say 40 and 25, then your minimum thickness is 19.5 and the maximum length is 58.5. So this is how the thickness gauge and the length gauge is being designed in IS 2386 to check the flakiness and elongation index of a material. The procedure to conduct the flakiness index test is: the sample is sieved with the set of sieves mentioned in the table in the previous slides in order to segregate the material. A minimum of 200 pieces of each fraction to be tested is taken and weighed. In order to separate the flaky materials, each fraction is then gauged for thickness on a thickness gauge. The amount of flaky materials passing the gauge is weighed to an accuracy of at least 0.1% of the test samples. To calculate the flakiness index of the entire samples of aggregates, first the weight of each fraction of aggregate passing and retained on the specified set of sieves is noted as a capital X1, X2, X3, etc. depending upon the nominal maximum size of the aggregate which is being used for the test. Like for example, if it is 20 mm sieve, then 20 down will be the set of sieves to be used to determine the flakiness index of the material. If it is a 26.5 mm aggregate, then accordingly you can use for WMM like 53 mm aggregate, then 53 mm down the set of sieves is to be used in order to segregate the material and the weight of each fraction passing and retained on the specified sieves. So the initial weights are being calculated as capital X1, capital X2 and capital X3. Each of the particles from this fraction of aggregate is tried to be passed through the slot of a specified thickness of the thickness gauge are found and weighed as small x1, small x2, small x3, etc. Then the flakiness index is the total weight of the flaky material passing the various thickness gauges expressed as a percentage of the total weight of the sample gauges. So thickness gauge or the flakiness index is the material which is being passed is being captured, and the ratio of passed divided by the total weight will give you the percentage of flakiness index. So this is the format generally used to calculate the flakiness index. So you have been given the set of sieves as prescribed in table 1 of IS 2386. So depending upon the type of the aggregate to be tested for flakiness index, like as we have discussed in the previous slides also, if it is a WMM or if your aggregate size is say 53 mm, then you probably start from 50 to 40, 40 to 25, 31 to 25 and 25 to 40, 25 to 20 and so on till 6.3 if the number of particle sizes are available, and under each fraction you should get at least minimum 200 pieces of samples, and then the weight of each slot is being captured as the initial weight, which is basically capital X1, capital X2, capital X3. The sum of the total will be the denominator of the formula to be used, and then the aggregate, each aggregate which is being passed is being collated for a set of sieves and weighed as the material passing through thickness gauge for a set of sieves, say 63 to 50 mm sieves. So that will be the total mass of sample passing the slots for a set of sieve given in table 1. So then the flakiness index is being expressed as the ratio of the passing material to the total material in terms of percentage, which is being denoted as the flakiness index of that particular sample. So calculation formula, if you see, the capital X1, X2, X3 will give you the weight of the samples being taken for testing, and small x1, small x2, small x3, that addition will give you the material which is being passed through the thickness gauge or the flakiness gauge, and the ratio will give you the flakiness index of the material which is being under test. Now coming to the procedure for elongation index test, the sample is sieved through the set of sieves, again the same set of IS sieves which is being specified in table 1. A minimum of 200 pieces of each fraction is taken and weighed. In order to separate elongated materials, each fraction is then gauged individually for length in a length gauge. The piece of aggregates from each fraction tested which could not pass through the specified gauge length with its long side are elongated particles and are collected separately to find the total weight of the aggregates retained on the length gauge for each fraction. The total amount of elongated materials retained on the length gauge is weighed to an accuracy of at least 0.1% of the weight of the samples. So how do we calculate the elongation index? In order to calculate the elongation index of the entire sample of aggregates, so first the weight of each fraction of aggregate passing and retained on the specified set of sieves is noted as capital Y1, capital Y2, capital Y3. And then each piece of these are tried to be passed through the specified length of the length gauge with its longest side, and those elongated pieces which do not pass the gauges are separated and weighed as small y1, small y2, small y3 and so on. Then the elongation index is the total weight of the material retained on the various length gauges expressed as a percentage of the total weight of the sample gauges. So using the same format which is being used for flakiness index, now instead of checking for flakiness, we will be checking the material for the elongation index. The method is same. You need to pass the material from each set of sieves, collect the initial sample of minimum 200 pieces, weigh it to get the initial weight as y1, y2, y3, and the sum of the weights will be the denominator of the formula to be calculated the elongation index, which is being shown in the bottom of the format. Then the mass of the samples being retained on the length gauge or the elongation gauge under each set of sieve is being checked and recorded. The sum of the mass or the samples retained on each length gauge divided by the total weight of the sample or the total mass of the sample in percentage will give you the elongation index of the materials. So to see the formula, the elongation index will be sum of the materials which is being retained on the length gauge or the elongation gauge, that is small y1, small y2, small y3, sum of those divided by the initial samples taken for testing, that is minimum 200 pieces of sample. So weight of that minimum 200 pieces of sample which is being recorded as capital Y1, capital Y2, capital Y3, the sum of those initial samples. So the mass retained on the length gauge divided by the total sample which is being tested for elongation gauge is being termed as the elongation index of the material being tested for shape. So what is we have tested till now? The individual flakiness index and the elongation index. But there is a term also known as the combined flakiness and elongation. So what is a combined flakiness and elongation, and how do we test it? Is it a combination of individually tested flakiness and elongation index, or it is different? Definitely it is going to be different, because when we say combined flakiness elongation, this is to determine the combined proportions of the flaky stones from a representative samples should be separated out. Flakiness index is the weight of the flaky stone metals divided by the weight of the stone samples in total, and only the elongated particles is separated out from the remaining non-flaky stone materials. That means when we test the elongation index, we need not use the original sample weight which is being tested for flakiness. Rather, we will use the non-flaky materials to be tested for elongation and then check what is the elongation index. So in that means your denominator weight will be the weight of the non-flaky materials. So the weight of mass retained on the elongation index gauge or elongation gauge or length gauge divided by the total weight of the non-flaky materials will be your elongation index. And flakiness index is the weight of the metals passing through the thickness gauge divided by the total weight of the samples being taken for the testing. So then the combination of these two will give you the combined flakiness and elongation index. So elongation index is the weight of elongated particles divided by the total non-flaky particles. The value of flakiness index and elongation index so found are added up to determine the combined flakiness and elongation index. So this is basically the observation sheet in order to determine the combined flakiness and elongation index. What is being done is you need to first determine the flakiness index for the materials being taken for testing. So weight of the aggregates taken under each fraction, again the limitation is minimum 200 pieces is required to be tested for flakiness index or thickness gauge. Then after determining the thickness gauge, you need to again find out the initial weight of the sample, which is basically a non-flaky material, and the non-flaky material which is being shown in the column F will be checked for the length gauge or the elongation index in column G, and the sum of those ratios will give you the elongation index. So the difference between the combined flakiness elongation and the conventional flakiness and elongation is the weight of the non-flaky materials. In the combined flakiness and elongation method, to determine the elongation index, we use the non-flaky materials, whereas in general, for determining the elongation index, we take the original weight of the sample as the denominator for calculation purpose. So the significance of flakiness and elongation index is flaky and elongated particles may have adverse effect on the concrete and bituminous mixes. For instance, flaky and elongated particles tends to lower the workability of the concrete mix, which may impair the long-term durabilities. It will have effect for cohesiveness of the mix. It will have an impact on the strength of the concrete mixes also. The figure shows the flaky and the elongated particles. Basically, flaky particles are like chips which are easy to break, whereas elongated particles are also the length to width, length to thickness ratio is too high. That is why they are said to be elongated, and it is easy to break the elongated particles individually. So in order to control the breaking of aggregates, you need to control the flakiness and the elongation of the aggregate particles. So these are the typical instruments which is being used to check the length gauge or the elongation of the materials. For bituminous mixes, flaky particles are liable to break up and disintegrate during the pavement rolling process and also during the application of the traffic. The effect of shape of aggregate on asphalt mixes, in particular, if you see, as the flakiness increases, the stability decreases and the flow and OBC values also increases. So if you see the table with different types of mixes like A, B, C, D, E on the extreme left, and all are having a different flakiness values starting from 5% to 45%. So if you see the stability column, the stability goes on decreasing continuously as the flakiness increases. The flow goes on increasing as the flakiness increases. The VMA also has a variation in terms of the change in flakiness, and the optimum asphalt content or the optimum binder content, which is being shown on the extreme right column, with the increase in the flakiness of the aggregates, the optimum binder content also increases. The same is the case with the concrete also. With the increase in the flakiness of the materials, the optimum cement content in the mix also goes on increasing. Like for example, if you want to have a design mix of a particular grade of concrete keeping everything constant, if you try to change the flakiness index of the aggregate being used in the mix, like for example, if the one mix is having a flakiness index of say around 15% and the other mix is having a flakiness index of around say 40%, then definitely the cement content in the second mix will be much higher as compared to the first one, which is having a flakiness index of 15%. So it is proved that aggregate types have the severe effect on the psychomechanical properties of concrete, as aggregate covers almost 70 to 80% of the total volume of concrete. The effect of flaky and elongated aggregates on strength, durability, and workability of concrete has often been qualitatively expressed. Generally, the limits of flakiness and elongation index, if you see for bituminous and non-bituminous mixes, flakiness index is maximum 15% and elongation index is also maximum 15%. But when you talk of a combined flakiness and elongation index for bituminous and non-bituminous mixes, it is maximum 30% and flakiness index for concrete mixes is maximum 35%. So to summarize this module, we talked about the definition of flakiness and elongation index, the definition of a combined flakiness and elongation index, how do we calculate individually the flakiness index and the elongation index, and how to calculate the combined flakiness and elongation index. What is the differentiator when we go for calculating the combined flakiness and elongation index? The main differentiator is when you are calculating the combined flakiness and elongation index, the elongation index is being checked for the non-flaky materials rather than checking for the complete samples. Then in this module we also talked about the significance of flakiness and elongation index in detail. In the next module we will be taking care of the specific gravity and water absorption of the aggregates. Thank you very much for watching. Do tune in for more updates.